Welcome to Hartman Math. Today we're going to take a look at vectors in the plane. So a vector is a quantity that has both magnitude and direction. Could be a force, could be a velocity. This is going to be very useful in physics. We often use to represent a directed line segment. So from geometry perspective, it kind of looks like a ray. It's going to have an initial point and it's going to have a terminal point. Now, unlike a ray, it does not go on forever. The arrow just shows the direction of the motion. So it goes from here to here. So here they're just showing some equivalent vectors. So any vector that goes essentially the same distance and in the same direction would be equal vectors. The symbol that we use, so we're going to start with, and it's very similar to a ray, the letter for the initial point goes first, the letter for the terminal point goes second, and the symbol for the vector kind of looks like a ray, but it only has the top part to the arrow. So that's the symbol for a vector. Often vectors can be written with lowercase letters like this, and in type you would see it usually bold or sometimes italicized. First way we're going to look at a vector is component form. So component form has what I kind of call pointy brackets here. And what we do to get that vector is we take the x-coordinate of the terminal point, Q1, and subtract the x-coordinate of the initial point, P1, comma, the y-coordinate of the terminal point minus the y-coordinate of the initial point. And so these are going to be numbers here inside of pointy brackets. And that's our vector. To find the magnitude, which can also be described as the length of the vector, it's essentially a Pythagorean theorem issue, is if we have those points, we kind of just use the distance formula. Or if we've got the vector itself, just square the two components, add them together, and take the square root. If the magnitude of the vector, and that's the notation here, is kind of like double absolute value bars, that means magnitude of the vector. If the magnitude of the vector is 1, then we would call it a unit vector. We're going to see that come into play later. If the magnitude is 0, then we're talking about the 0 vector. Example number 2, find a component form when we have the initial point and the terminal point. So we're going to use our formula here. We're going to say that the vector v, bold V, equals pointy brackets, terminal 3 minus negative 1, comma, 2 minus 6, always terminal minus initial. And if we just simplify those, we get the vector pointy brackets 4 comma negative 4. Essentially what that means is the vector travels 4 right, but at the same time down 4. So something like this. Second part to that, find also the length, and that does refer to the magnitude of the vector. We could do it from here, but since we have the vector itself, might as well just do the square root of the 4 squared plus the negative 4 squared. And you would get the square root of 32, which does simplify to be, in simplest radical form, 4 root 2. We can perform vector operations. We can do it graphically as well as algebraically. We'll show both of those. Graphically, when we're talking about vectors, they can be anywhere, but it's most logical to have the initial point be the origin. So vector u is the vector negative 2 comma 5, meaning go left 2 and up 5, left 2, up 5. There's vector u. And vector v is pointy brackets 4 comma 2, right 4, up 2. So those are the two vectors. starting there. So to add them, what we can do is take, and since addition, the order doesn't matter, we can take either vector, pull it off of here, and then replace it where you terminated, have v be initiate from there, and go right 4 and up 2. So we'll just kind of relocate that vector, and it goes there. And then, so the sum vector would start where u starts, and then it's going to end here. And like I said, we could have pulled the u off and put it here. Either way, we're ending at the same spot. That is the sum vector u plus v. If we want to do it algebraically, it's extremely easy. Addition, add the two x components, add the two y components, and we get our vector that went right 2 and up 7. That's the sum vector. Subtraction's a little bit more challenging. As we know from regular subtraction of numbers, order does matter, so we can't just do it any way we want to. But one of the ways you did learn about subtraction is to think that it's adding the opposite. So u minus v is the same thing as u plus the opposite of v. And the opposite of v means go the same length, just in the directly opposite direction. So instead of going right 4 up 2, let's go left 4 down 2. That would be negative v, or the opposite of v. And then we can add that to u by moving it to here. And then our difference vector starts here and ends there. U minus v. And if we do it algebraically, same thing. Order matters here. Negative 2 minus 4, comma 5 minus 2. We get the vector, pointy brackets, negative 6 comma 3. Go left 6, up 3. Example 3, vector operations. So there's two different kinds of multiplication within vectors. This is one of them, and this is scalar multiplication, which means take a number, 2, that's our scalar, and multiply it by v, the vector. So in this case, we would just double v. So in that direction, just go twice as long. We double it, we're going to end up here. And that's the same thing as essentially distributing that 2, multiplying both parts by the 2, both components. And you would get the vector 2v is equal to the pointy brackets 4 comma 6, right 4, and up 6. So just a summary of what we just looked at in some of the addition and the multiplication. Okay, unit vectors. This is really important to be able to initially find a unit vector. So what it's saying here is a unit vector for any vector v. Take the vector v and scalar divide by its magnitude. It's just another version. So that's going to be our approach. Find the vector v, or maybe we'll know that, divide scalarly by its magnitude. All right, example 5, find a unit vector for this vector. Step 1 would be to find its magnitude. So go ahead and pause here, find the magnitude of vector v. And from previously, the formula would be the square root of the sum of the squares of the components. So we would get the square root of 34. So now to get the unit vector, which would be v over the magnitude of v, we're just going to take our vector and divide by the magnitude. So we would get pointy brackets 3 over square root of 34. No, you don't have to rationalize that. If you want to, that's fine. We get 3 root 34 over 34 in that case, comma negative 5 over square root of 34. one more question before we move on. What is the magnitude of that vector that we just got, our answer? Think about that. And its magnitude, if you want to, you can go through the process of finding it, but I don't think we need to do that. Its magnitude is 1. That's the definition of a unit vector. The magnitude is 1. All right, example 5 plus. And this is really the power of the unit vector. Write a vector that's in the same direction as this one with a magnitude of whatever we want it to be, in this case 8. First, find a unit vector. For the vector in question, we just did that in the last problem. And then since that's a magnitude of 1, but we want a magnitude of 8, just scalar multiplication with the 8. So 8 times the unit vector for that vector is how we would get there. So multiply by 8, we get our final answer, 24 over the square root of 34, comma, negative 40 over the square root of 34. So in summary, find the unit vector, which will have a magnitude of 1. Then you can multiply it by whatever magnitude you want to get to the desired magnitude. All right, some other notations. Standard unit vectors, the vector I, not to be confused with the imaginary number. So this is as a vector, again, bold typeface, I, is the vector go right 1. And j is the vector go up 1. So this is just different component form with i's and j's, kind of thinking in terms of algebraic expressions. So this is the horizontal unit vector. Here is the vertical unit vector. We can write any vector as a linear combination of those. There will not be a comma. There will not be pointy brackets. Not in this form. All right, let u be the vector with the initial point, negative 1, comma 8, and the terminal point being 3, comma 1. Write it as a linear combination of i's and j's. So again, we would do the same process we did earlier. Terminal x minus initial, so 3 minus negative 1, 1 minus 8. Okay, so that vector in the pointy bracket standard form would be 4, comma negative 7. Now, how do we write that as a combination of i's and j's? Here are the i's, here are the j's. So 4i minus 7j, no commas, no brackets, just a linear combination. Therefore, it looks like an algebraic expression. Let u be this vector, which is a combination of i's and j's, and v be this vector, combination of i's and j's. Find the vector 4 times u minus 3 times v. It's just an algebra problem. So all we need to do is do 4 times this expression minus 3 times this expression and do it algebraically. So distribute, distribute, combine like terms. And there's our final answer, vector 24i minus 26j. In other words, 24 to the right, 26 down. That's the vector that we're describing. All right, so now we're going to get into some of the trig stuff and how it connects to vectors. Direction angle. So if we have u be a unit vector with x and y as the components there, we do know if it's a unit vector, we kind of connect that to the unit circle. So if we're talking about one away, and then back from the unit circle, x was the cosine of theta, and the y was the sine of theta. If we wanted to do it in terms of i's and j's, cosine theta I plus sine theta j. So theta is the direction angle. We can think of it in terms of, it's a trig angle of our vector u. So one way of writing the vector in component form is the magnitude of vector v times the cosine of theta, comma the sine of theta, if we know the direction angle. Now if we're trying to find the direction angle, we can use the tangent theta is equal to sine theta over cosine theta identity, the quotient identity there. So the sine of theta, if we go back here to the unit circle idea, that's just the y-coordinate and cosine theta being the x-coordinate. So in terms here of our vector, if we're talking about in component form, whether it's pointy brackets, a comma b, or ai plus bj, the y divided by the x, so tangent theta is going to be b over a. That's how we're going to find it. So if we know that, to find theta, we'll do inverse tangent b over a. Now the one thing you got to worry about here, again, is the limitations of the inverse tangent on your calculator. When you type that in, it's only going to give you an answer in quadrants 1 or 4. Think about our vector. If it's in quadrant 2, meaning go left and up, then we're going to have to take our vector 4, add pi to that. If we're talking about in terms of radians, if we're talking about degrees, add 180 to get into quadrant 2. Same thing if we had a quadrant 1 answer here, but we know that our vector is in quadrant 3 because it goes left and down. Add 180 degrees or add pi to get the correct direction angle. Find the direction angle of each vector. There we go for vector u, which is not a unit vector. We can tell the magnitude would not be 1 there. But that's irrelevant. We could say tangent theta would be 5 over negative 5. So tangent theta is negative 1. I don't think we need a calculator on this one. That's a unit circle value where is the y-coordinate and the x-coordinate differing sign, but the ratio is the same. So that's either going to be in quadrants 2 or 4. Well, let's look at this. Go left and up. That's going to be quadrant 2. So we're thinking quadrant 2, 45, 45, 90, special right triangle, or 45-degree reference angle. If we're talking about in terms of degrees, that would be 135 degrees, or 3 pi over 4 radians. All right, part B. Tangent theta equals negative 7 divided by 2. That is not a unit circle problem. So we're going to need to type that into the calculator. Now this one's going to go right and down. So that would be quadrant 4. So it's going to give us a quadrant 4. And that would be okay. But sometimes we may want everything between 0 and 360. So since we're in the correct quadrant, but we want a positive answer, let's go one more rotation around, add 360 to that. We could say it's 285.95 degrees if it's specified that it needs to be positive within one rotation. Without that, this is not a bad answer, but usually a little bit more universally accepted here. All right, example 9 is going to be our last part to this lesson. It's going to show how vectors can really help and simplify problems. So we've got an airplane flying in calm conditions north 26 degrees west at a specific velocity. The plane encounters a wind, a pretty severe wind. Find the ground speed and the bearing of the airplane. So ground speed means what we would observe from the ground. after the wind has influenced what it is. The airplane vector is going to be no wind influence. So we're going to look at airplane vector, we're going to look at wind vector, and we're going to get ground speed. And it turns out that in terms of vectors, the airplane vector plus the wind vector will equal the ground speed vector. So we have, it's also would be the same as if we had two forces acting. The resultant force is if we add those two forces together. All right, so we're going to start with airplane and take a look at that. We're flying north, and we're going to bend 26 degrees towards the west. So there's our airplane vector. It does have a magnitude of 350. And then we've got a wind vector, north, 70 degrees towards the east. So here's our airplane vector, 350 times, here's our unit vector. Get that from the trig. Keep in mind, it needs to be a trig angle. So we're not using 26. It needs to come from there. So it's 90 degrees plus the 26 degrees. That's where we're getting the 116, a trig angle, which is our direction angle. So approximately that vector means our plane is essentially traveling 153.43 miles per hour going west, and at the same time 314.58 going up, or in this case north. So now the wind vector is there, and we're going to do the same thing here. 70 as the 60, which is the magnitude, times cosine of the direction angle, which is this angle, 20 degrees. And then if we add those two vectors, add the components, we're going to get the ground speed vector. There's our ground speed vector. So we want to know the ground speed itself, not the vector, and that's going to mean the magnitude. So next, pause here, find the magnitude of that vector. So the magnitude of the ground speed vector, use our formula, that's going to be about 349 miles per hour after the wind is influenced. All right, so now what's the new bearing now that the wind is pushing it? Well, we can use this vector and find the angle. So inverse tangent. And we would get theta is about 106.2. Now it's not telling you that. It's telling you probably something that's negative in that case. But if we look at our vector that says go left and up, that's quadrant 2, and the one that your calculator is telling you is quadrant 4. So we need to add 180 degrees to it to put it into quadrant 2. 106.2 degrees, so that's past 90, so we are definitely into quadrant 2, where we are going north, and since we're going to the left, we're going to go west. How far past 90, because that's our north line, is this? 16.2 degrees past 90. We always reference our bearings to north or south. So that's 16.2 degrees past the north line. And there's our answer. That's it for today. I'll see you next time.